Let's look at compound interest compounded annually. Suppose you get a graduation gift of $1,000. You deposit it into an account which grows at 5% annual interest compounded annually. How much do you have in 40 years? Well, here's the formula we're going to use. If we deposit P dollars for example, into an account which grows at an annual interest rate of R is expressed as a decimal, compounded annually, then after T years we will have F equals P times 1 plus R to the T. Looks complicated, but you'll get used to it. Okay, so in this case, F. F is our future amount of money, and we don't know what that is, so that's just a question mark. P stands for principal, or present. That's what we begin with. In this case, we begin with $1,000, so P equals 1,000. R is the interest rate expressed as a decimal. Do not write R equals 5. You'll get the wrong answer. When you express 5% as a decimal, you get 0.05, so R equals 0.05. T in this case is 40. T is the number of years, so we're talking about 40 years. T equals 40. Okay, so plug everything in. F equals P times 1 plus R to the T, which is 1,000 times 1 plus 0.05 to the 40th. If I type this into my TI, 1,000 times 1 plus 0.05 to the 40th on my TI-83, and press enter, I get this answer, $7,039.99. Not bad for just a $1,000 investment. Okay, suppose you want to take a blockbuster vacation 30 years from now. Suppose you want to have $15,000 in order to do this. How much do you need to set aside today if you want to have $15,000 in 30 years? Assume your investment grows at 7% annually. Okay, so again, we're going to use the same formula that we had before, F equals P times 1 plus R to the T. Okay, in this case, we have the reverse. In the previous problem, we did not know what F was, but we did know what P was. Here, we know what F, the future amount, is. That's $15,000. What we don't know is P. We don't know the present amount that we should set aside. So P, that's just a big question mark. Okay, again, we have R equals 0.07, 7% interest. T equals 30 years. Plug everything in, and we get 15,000 equals P times 1 plus 0.07 to the 30th. Again, we're going to have to simplify this somehow. So what we do is divide both sides by 1.07 to the 30th, and we end up with 15,000 divided by 1 plus 0.07 to the 30th. That equals P. And if I plug this into my TI, I get $1,970.51. Besides growing bank accounts, we can also use these formulas to analyze growing populations, or prices which grow at a certain rate of inflation. For example, in the April 2010 U.S. Census, the United States population was 308,745,538. In recent years, the U.S. population has grown at an annual rate of 0.9%. If this trend continues, estimate the U.S. population in 2020. Okay, again, we're going to use the same formula, F equals P times 1 plus R to the T. So whether it's interest that's compounded annually, or growing populations, or inflation, we use this formula. Okay, F, we don't know. We don't know what that future population is going to be. We know the present population. There it is, 308,745,538. We know the interest rate, or really the rate of increase, 0.009. Now be careful. It's so tempting to say, okay, in this problem, R equals 0.9, but that would be wrong. Because if the increase expressed as a percent is 0.9%, the way we'd express that as a decimal is 0.009. So don't enter R equals 0.9. That's wrong. Okay, in this case, T equals 10 years. Plug everything in. F equals 308,745,538 times 1 plus 0.009 to the 10th. And we end up with 337,685,453 people. We can use the same formula if we want to calculate the cost of something that rises by a certain percent each year. For example, if the cost of cable TV increases 5% each year, and we know what cable TV costs now, we can use this formula to find the cost of cable TV 10 years from now.